Good morning. Happy Monday. I hope you are well. Today is class presentations day. Woohoo! All right, nobody can get too excited. But anyway, I'm looking forward to your class presentations. Should be really cool. You've all done some cool work. I've heard little bits and pieces about them. I'm anxious to see it in action. So 2501 today. We'll start right at 110. It's a smaller class. It won't take that long. No labs, problem sets, or anything afterwards, so it should be pretty chill. Your paper's due at the time of the class presentation, as long as the titration of weak acids lab. One thing that I've talked with several people about over the weekend, I just want to state, if you are a Mac user and your presentation is in Keynote, please realize that our Windows computer doesn't do Keynote. Fascist. Anyway, if you have Keynote, though, export as a PowerPoint, and then you'll be good to go. All right? So if that applies to you, cool. But if it doesn't, you can ignore what I said, and don't worry about it. Questions on it? All right. We left off on Friday talking about formation constants, which are equilibrium constants for complex ions. A complex ion is when you have a Lewis base and a Lewis acid coming together. In this context, the complex ion Lewis acid is almost always a transition metal. You can have lanthanides and actinides, aluminum boron, gallium, those kind of things, but it's almost always transition metals. The Lewis base is just anything with lone pairs on it. Ammonia, cyanide, water, hydroxide, there's a whole bunch of different ones. And these things look weird to me, all right? But how a complex ion formation constant is created is the complex ion is the product, and whatever ions or molecules that go into it, those are the reactants. So for this weird thing here, AgCN2 minus 1, that would be the product, and it has a silver plus and 2 cyanides to make this overall minus 1 charge. So that's the formation constant equation. The equilibrium constant then will have the complex ion exclusively in the numerator, and in the denominator you'll have whatever ions or molecules go into it. So this will be silver plus and cyanide squared. These K values are really, really big, very, very product favorite. These are the ones that made the chemists nervous when their solids disappeared. And in the Le Chatelier's principle, you saw the zinc hydroxide go away when you added extra hydroxide or ammonia. That's because the complex ion kicked in. Magnesium hydroxide didn't disappear because magnesium doesn't have the right kind of orbital set, but zinc absolutely does, and it can get kind of crazy. So this is just a table of these values. Again, look at some of these numbers. Very, very product favorite, all right? These want to form when they're around. And there's some good things you can do with them. If you don't know how they work, they can be kind of frustrating, but they can be really cool. But in all of these, whatever you're writing, the complex ion will be the product, and whatever goes into it is going to be the reactants. So we will actually see, or actually not see because it'll disappear, but we're going to see, if you will, this compound right here, this nickel compound with 6 ammonias. It's got a very product favored K, so if we were going to write the expression for it, this compound right here would be the product. We would have 6 ammonias, and a nickel 2 plus would be the reactants. So you can figure out what all of them are. They're almost always written as net ionic reactions, so we're not including the sodiums or potassiums that go with the cyanide. We're also not including the nitrate or whatever ions go with the silver. We're just showing the action of the reaction to really focus in on what's happening. You don't have to memorize any of these, just realize they're out there, and if you see them, cool. This is a real practical use of a silver complex ion that we use here at Mount Hood. Silver chloride is really insoluble, as we've talked about, and it will stain glassware. So if you look at some of our glassware, some of it has kind of a white stain on it, and most of the time that's a silver chloride. But if you add some ammonia, the ammonia makes a complex ion with the silver. So it takes away the silver chloride solid, at least to a point, and makes a soluble compound so you can wash it off your glassware, stuff like that. If you wanted to know how this works, you could find the KSP for silver chloride after this section, which is just in a table. Remember the KSPs, the solid is the reactant, and the ions that go into it are products. However, for a complex ion, the complex ion is the product, and the ions that go into it are the reactants. So the one thing I'm going to highlight for you once again is that KSP and KFs are kind of opposite. Like if you have a KSP for silver chloride, the silver chloride is the reactant and the ions are product. But if you have a KF for this AgNH32 thing, that's going to be the product, and we'd have Ag plus and 2 ammonias as reactants. Anyway, if you combine these two reactions together, you can see how the silver ion goes away. And you're going to have a complex ion and chloride, and it does allow a lot of this white film stuff to go away.
When solutions of silver nitrate and sodium chloride are mixed, insoluble silver chloride precipitates from solution. When we add ammonia to the mixture, however, the precipitate redissolves. When ammonia is added to a mixture of solid and aqueous silver chloride, the ammonia serves as a Lewis base. The complex ion formed consists of 2 ammonia molecules bound to each silver ion. Formation of the complex lowers the concentration of silver in solution, which changes the solubility equilibrium.
So this whole chapter we've talked about KSP, and if you have a silver chloride compound like right here, you have a lot of solid, but you also have dissolved silver and chloride ions floating around. So when you add ammonia, like in this case, the ammonia tends to react with the silver. It pulls some of the silver out of the solution, and that makes some of these silvers that go up, because it's always about equilibrium, and equilibrium means no zero of anything, basically. So it pulls the silver ions out. You have more chloride running around, but if you wanted to get rid of that white film silver chloride, that's kind of cool. Here at Mount Hood, the unknown chloride lab from Chem 221 creates a lot of silver chloride. And so this is a great way then to get rid of that film so our purettes look brand spanking new. Questions on anything? Okay, so that's it for chapter 15. Chapter 15, as I talked about, is not perhaps my all-time favorite chapter, but it is really good because it talks about then how equilibrium works with solid and stuff like that. But now what we're going to do is we're going to talk about probably one of my favorite chapters, which is chapter 16. And all of the chapters we've seen so far in chemistry kind of come together in this chapter right here. And so this chapter is real powerful if you want to know if a reaction is going to occur or if it won't occur, or if you want to know if a reaction is possible to change at different temperatures, stuff like that. Now, so far in chemistry, we've talked a lot about enthalpy. But there's another player in all of this, and I've mentioned it a couple times, and it's called entropy. And entropy is very, very fascinating as a concept. And I think this little comic here shows entropy super well what it's all about. And if you look at this comic, the door is off the hinge, only one hinge is on and the other one is off, okay? And you can see that the date on the calendar is 1967, which certainly is not today. You know, the trash can is spilled over, the desk has some books on it, there's a hole in the floor, et cetera, et cetera. And that's really what entropy is all about. Entropy is messiness, disorder. And if you live with someone who has gotten after you, clean your room, all right? Well, you can now explain to them after taking Chem 223, that you are just following entropy. And believe it or not, entropy is one of the major players in how the universe works. So it's really interesting. We're going to talk about how entropy and enthalpy, they kind of fight each other for dominance. And if they both agree with something, then those reactions are going to go all the time. But sometimes they fight each other, and only the one that wins gets to decide if something happens. And sometimes you have reactions which don't go at all. And that's because both enthalpy and entropy don't happen. So we're going to start talking about in this section when reactions will occur and when they won't occur, absolutely, which is really cool. However, if you have a reaction which doesn't occur and you really want it to occur, Chapter 17, which is going to get into voltage, electricity, electrochemistry, that's sometimes a way to sneak around thermodynamics. And we'll talk about that then. So while chapter 15 was a little slow and dry, shall we say, I think chapter 16 will be a little bit more interesting, so hold on. Questions? Okay. Now, let's review real fast some important things here. Thermodynamics and kinetics, I would argue, basically dictate how chemistry and most of physical science works. Thermodynamics is kind of a yes or no option. When you know how thermodynamics works, you can tell if something's going to occur or when it won't occur. So for example, paper will burn, all right? Absolutely. Thermodynamics, it wants it to burn. We're going to see that's something that's going to happen. However, thermodynamics doesn't say anything about the time that it takes for a reaction to occur. So the paper isn't probably going to spontaneously combust right now, but it will given enough time. And we've talked about, if you've been with me since Chem 221, we've talked about how diamonds are thermodynamically, they're going to go to graphite. But it takes lifetimes upon lifetimes for it to happen. So you don't have to go sell your diamonds or anything like that. Kinetics is the study of time with science, all right? And kinetics is also really important to talk about in this section. We're going to talk here a lot about reactions that will occur and won't occur, all right? Yes or no. But if you have a reaction which is going to occur and it makes you nervous, think about the kinetics, all right? Because some reactions take a long time. Now in our labs, the reactions are fast, all right? We only have a couple of hours. You don't want to be there until 5 o'clock, et cetera, et cetera. So they have to go pretty fast, and that's what we're used to. But in the real world, you have geologic time, which, man, can go on for, or astronomical time. We have to think about the time involved to make these reactions occur as well. So in the back of this whole conversation, think about kinetics. Okay, this is something we looked at in the kinetics chapter in Chem 222 if you were here. And if you haven't, this is called a reaction diagram. Energy is the y-axis, and the progression, if you will, of the reaction is on the x-axis. And usually how this works is reactants are on the left, products are on the right. This particular reaction, the products is higher than the reactants. Does that mean that's endothermic or exothermic? Endo. Nice job. Nice job. If the products are higher than the reactants, then it's going to take a net amount of energy to go from reactants to the products. So this is an example of an endothermic reaction, which means you have to put energy in. If the products was like down here, then reactants would be higher and products would be lower. That would be an example of an exothermic reaction. But more importantly here, there's something called the energy of activation we talked about in Chem 222. And it's the energy to go from where you start to the top of the hump, basically. And that's also an energy cost. Now you get some of it back out when you go down to products, whatever that is. But this is where kinetics plays a factor. All right. If you have a super high kinetics, energy of activation, the reactions will be slow. On the other hand, some things like burning paper, like you go up here and then down, it's a much lower energy of activation, so it goes a lot faster. Any questions on that?
Now, will the two of you please get out of here and leave me alone?
You're wasting energy, Mr. Plummer. Relax.
I apologize for the bad science fiction references here.
He's a scientist. He knows energy must not be wasted.
And time. Energy and time are two most precious possessions. You don't have to worry about me, Janet. I'm fine.
So the scientist kind of lost his equilibrium, if you will, and forgot that the most important things are energy and time. And that's totally what this is about. Energy, thermodynamics, and time is kinetics and stuff like that. Super. Anyway, that's from The Outer Limits.
Oh, yeah.
All right. Cheesy science fiction from the 60s. You don't have to like science fiction even to do it, although you should get out of my class. No, I'm just joking. You know me by now. This is how I roll. Anyway. First law, thermodynamics. We're going to talk a lot about thermodynamics and stuff like that. And the first law of thermodynamics is really what we've been dealing with in chemistry since the very first day of Chem 221. And this is probably one that you know, even if it's not formal. The first law just says energy can't be created or destroyed, all right? So all the energy that goes into the reaction has to be accounted for on the way back out, all right? Now, formally, they write things like this, where it shows the change in the energy of the universe. And there's no change in the energy of the universe, according to the first law, all right? All the energy that's here is constant. It gets rearranged, but you're not making or destroying any energy. And there's two things, and we'll talk about this later, the system and the surroundings. In Chem 221, we talked about how the system was like the chemical reactants that were actually reacting together, and the surroundings was like the solvent or the air or the gas or the container around the chemical reaction. And so sometimes you have rearrangements, like the energy from the system goes to the surroundings or vice versa, but the overall energy is the same, and that's really important. Now, when you think about all the energy that's known, most of the energy comes up through what's called heat and work, all right? And in Chem 221, if you were with me, we talked about that real briefly there. Work is really important when you have an engine, pistons, and stuff like that. Honestly, chemists don't worry as much about work. Sometimes you can have like carbon dioxide expanding, lifting a book or something. That's a classic teaching example. But most of the time, the chemists just think about heat, all right? Heat energy is the exothermic and endothermic we talked about. And if the energy is transferred at constant pressure, that's where enthalpy plays a factor. And up until this point, enthalpy, which gets the symbol delta H, that's been the important part. We've talked about if you have exothermic, endothermic reactions and stuff like that. So anyway, this is a terrible thing about mother-in-law. Of course, it's not relative to me personally. I'll have to edit that out in the video later. Anyway, questions on the first law of thermodynamics? Don't ask me any personal questions on that. I'd be embarrassed. All right. Oh yes.
And now, maximum energy.
This is from, what's that movie? It's the worst movie ever made. Plan 9 from Outer Space and stuff. So anyway, this guy is one of the people in there. Again, sorry for the bad references, but this chapter definitely lends itself very well to bad media references. Okay, here's a little flashback from Chem 221, enthalpy, all right? And so again, I'm sure you saw enthalpy somewhere along the way, but just in case, make sure we're all up to speed. Here we go. Enthalpy gets the symbol delta H. It's usually in kilojoules per mole, sometimes just joules. It's all over the place. If you have a negative delta H, that means it's exothermic. Energy's being released by the system. So if you have a reaction and it feels hot, that's because the energy is being released and you can actually feel the energy like coming up. That's very common for reactions that happen. On the other hand, some reactions, you feel them and it feels cold. Those are endothermic reactions. Positive delta H is what is kind of sign you'll see right there. Now in Chem 221, we looked at Hess's law, which is when you have a couple different reactions and you combine them to give an overall reaction. And also this one, which is probably more important, the way to find the delta H for a reaction is you take the sum of all the delta H's that are products and you subtract from it the sum of all the delta H's that are reactants. And you need values like these right here. These are called formation enthalpies. There's a table in problem set 5 that we'll use, which has a lot of these in there. None of these are things you have to know. That little F right there is the standard. It means per mole of product, basically. We also looked in Chem 222 at what's called a bond enthalpy, which is when you have like bonds broken minus bonds formed for reactions when you know the Lewis structures. Those could be helpful too. Again, none of these numbers or anything you have to know. Just kind of trying to have a little flashback here as to all these things, how they work out. Any questions on this? If you look at like this equation and you're like, what the? All right, let me know, all right, because I have some resources and stuff to kind of refresh your memory. It's in your mind. We just have to bring it off the top shelf and dust it off a little bit. We'll be good to go. Okay. Now, another thing we're going to start talking about is called a spontaneous reaction. Now, spontaneous has a science meaning, which is different from the meaning that I would use in my day-to-day life. So, for example, I saw that the Godzilla was still playing at Star Trek. I'm like, hey, Jacob, let's go see Godzilla. That would be spontaneous, right? Blowing off classes, not being practical. That's a fun way to think about, if you like seeing Godzilla. That would be a fun way to interpret spontaneous, but it's different in science, okay? So, darn it, I'm not really going to go see Godzilla today. I do want to see your presentations. Anyway, spontaneous just means that you have a product-favored reaction, all right? You're going to see something happen. It has nothing to do with spontaneity, like going and doing something random. That's more about time, all right? Like we're just going to spontaneously go to the mall, all right? Ooh, that sounds fun. But that's different than science. Spontaneous reaction just means that something happens. It's product favored. Now, product favored in equilibrium this chapter means that your K value will be greater than 1. So a spontaneous reaction means that you're going to have a K value, an equilibrium constant greater than 1. Could be a Ka, it could be a Kf, Ksp, all right, any of these kind of things. Spontaneous is that way. Now, most product-favored reactions are exothermic, which means that heat is released in the system. Not all, as it says there, but generally speaking, that's the case. And up until this chapter, if we wanted to know if a reaction will occur or won't occur, I would have said, well, we'll see if it's exothermic, endothermic. And if it's exothermic, it'll be probably spontaneous. It'll happen. If you had an endothermic reaction, probably it won't happen. So again, spontaneous just means it's going to be product favored. You're going to see something happen. It doesn't mean you're going to do something spur of the moment. Is that cool? All right. A non-spontaneous reaction is something that's going to take energy to occur. It's something that won't occur by itself. All right. So all of the K values that have been less than 1, which is honestly most of them, Kas, Kbs, Ksps and stuff, those are all non-spontaneous, which means they don't go naturally from reactants to products. They need extra energy to happen. And extra energy usually comes in the form of energy of activation, that kinetics thing. So spontaneity, all right, once again, it has nothing to do with time or changing your plans or something like that. It just means that a reaction will occur. It's product favored. Non-spontaneous means the reaction won't occur. Spontaneous means K is going to be greater than 1. Non-spontaneous, K less than 1. And remember, we still have to think about kinetics in the back of our mind as to how fast or how slow things will go. Because thermodynamics is going to say, yes, diamond to graphite, spontaneous. But it doesn't mean it's going to happen right away necessarily. And that reaction is super, super slow, thousands of years. Cool. So, first law of thermodynamics doesn't say anything about if a reaction will occur or not, all right? It just says that you're not going to create or destroy any energy. And we'll start talking about how to tell if a reaction is spontaneous or product favored or non-spontaneous reactant favored. Questions? Okay, so here's an example of a spontaneous reaction. You leave a nice iron nail outside and it rains like it has been doing here for a long time. All of a sudden, it goes rusty, all right? That's a spontaneous reaction. It happens. Now, most reactions which are spontaneous in one direction will be non-spontaneous in the other. So the iron nail that goes rusty, that's spontaneous, it's gonna happen. But your non-rusty nail, going back to that, that's not gonna happen. That would be considered non-spontaneous. So almost always one direction is spontaneous and the other direction is non-spontaneous. Now, like I said, there are some reactions which are going to be spontaneous, but they take forever. So always remember that kinetics is a player here. And diamonds, once again, are going to turn to graphite, but man, it takes thousands and thousands of years. So nobody has to go sell their diamonds or anything like that. On the other hand, if you burn that paper, boy, that's going to happen. That's easy to do. And that's going to be fast, all right? This is kinetically favored. This reaction is not kinetically favored. So always keep kinetics in the back of your mind. Both of these reactions are going to happen. It's just that this one happens in an appreciable amount of time in our lifetime, while this one would not unless you accelerate it somehow. Question? Okay. Now, there's also a temperature dependence for spontaneity, and the best example of that is ice and liquid water. If you have a temperature which is less than 0 Celsius, your liquid water will freeze, all right? That's going to happen spontaneously. You don't see the ice melting if you're under 0 degrees Celsius. On the other hand, if you're at room temperature or above 0, your ice cubes will melt, and that'll be spontaneous. And I have yet to see above 0 degrees Celsius, under normal conditions, liquid water start to freeze spontaneously. You have to put it in the freezer. So there's a temperature dependence to all of this as well, which is just one more factor to think about in the back of your mind while we go through this. So spontaneity has a temperature dependence. It's usually one reaction is spontaneous one way or the other way at a given temperature, but then you can shift the temperature too. Okay. A reversible reaction is something else to think about. Some reactions can have reversible conditions. So for example, if you have some reaction in a system and it creates heat to enter into the surroundings, once in a while you can have that be an opposite factor too, where the opposite happens, where the heat is pulled from the outside in to go back to the system. If you have a rechargeable battery, that's actually pretty cool because those kind of things don't happen a lot. Like you can't have it go one way and then back the other way under normal conditions. All right, usually there's like a one directional kind of way which is preferred. So it's not impossible, but it is pretty rare. If you take sodium metal and you put it in water, boom, all right, lots of energy is released. But it doesn't go back to normal sodium metal under normal conditions. And that's the hallmark of most reactions. Okay. Irreversible processes cannot be undone by just reversing the change in the equilibrium. So here's your nice car, you let it outside long enough, it goes rusty. You can't, by any means necessary, that I know of anyway, take a rusty car and turn it back into a nice car. You'd have to buff it out, paint it, whatever you do to cars and stuff like that to make it go back this way. So again, one reaction is going to happen in one way, and it usually doesn't happen in the other way. Usually spontaneous reactions, I would say, are irreversible. You're going to go one direction will be easy, but the other direction will be harder. Okay. So this leads to the directionality of reactions. Like, how do you know how likely it is if a reaction is going to occur or not occur? And this is a question that all scientists in chemistry and physics have thought about for a long time. And let's phrase it now, though, in our new language. We want to know how probable it is that reactant molecules will react to make some new product. We want to know how spontaneous it is. We want to know how likely it is that you can have a spontaneous reaction. And it's really interesting. People have studied these kind of reactions, and they look at them with statistical methods. And most of the time, if you have a spontaneous reaction, your spontaneous reaction will involve dispersal. Dispersal means taking something concentrated and kind of making it less concentrated. And there's two types of dispersal that we see, that is seen in chemistry. You see energy dispersal, so you have a concentrated form of energy, and the energy then is distributed to the universe. You also have matter dispersal, matter coming together and then going to like messiness, matter all over the place, or you can have both of them together. So let's think about a gummy bear, all right? Gummy bears, small little, tasting good. That's one of my weaknesses. Anyway, sound effects not necessary. You have a little tiny gummy bear, all right, and you eat it, all right? Well, first of all, biologically, biochemically, that little tiny gummy bear, those sugar molecules, whatever, are going to be distributed through your body. And when it comes out the other side, of course, it's a lot different. You no longer have the concentrated gummy bear, all right? The gummy bear has been broken down into different compounds and stuff like that. Your body gets rid of it as waste. But another product of the gummy bear is the energy, all right? Because the sugar involved kind of, whoa, one time, long story short, I did way too many gummy bears. I was like, whoa, for a while, but then I crashed afterwards. All right, really brought that back on now. Anyway, energy dispersal is also really important, all right? Several of you have Monster drinks and stuff in the morning. Yeah, no problem. I understand. Coffee's my drug du jour, but it's the same thing. You take that in, man, to give you a little bit of a kick and stuff to go. Completely legal, no problem. And then some things you have energy and matter being dispersed, all right? The first person to propose this was a guy named Boltzmann. Boltzmann's a real interesting person. On his tombstone, he has written S equals K log W, and we'll talk about that here in a little bit. Boltzmann's kind of a wild dude. There's a Boltzmann constant in physics. We won't talk about it in chemistry, but it is pretty interesting.
Very off topic. Is that a V or a U? Or is it Ludwig?
Yeah, it's Ludwig, but they did it like old Roman style.
Okay.
Don't let
I know
it
it's off
lie.
topic. I was just kind
No, that's a good question, man. Boltzmann's an interesting person, but yeah, it is supposed to be a U, and they did it the old Roman style, I guess. So, yeah. Anyway, so summarizing how important this is, people looked at all reactions, acids and bases, gummy bears in your body, caffeine in your bloodstream, et cetera, and the reactions which occur, all right, have some kind of dispersal. You either have a lot of energy concentrated and then it's distributed through your body, like the caffeines and stuff like that, or you have matter that's very concentrated, like a sugar cube, and it's distributed through your body, or you have both, all right? There's not a lot of examples where energy is all over the place and it's concentrated, or with not a lot of examples of matter all over the place and it's concentrated. It's usually the opposite, all right? Making this very concentrated become more dilute. Questions? Okay.
Consider a pair of flasks, one containing gas molecules, the other completely empty. If the flasks are connected at their mouths, gas in the filled flask will move spontaneously to the empty flask by its molecular motions. Eventually, the distribution of molecules will be even throughout the flasks. The final state in which the matter is more dispersed is much more probable than the initial undispersed state.
In Chem 222, we talked about diffusion and effusion of gases. This would be an example of diffusion where one gas was on one side and a vacuum on the other. And there's a natural tendency for the gas to want to go to the other side. So at the end, you don't have like all the gas on the right side, all right? But what you have then is an equally distributed, more or less, gas thing on both sides, all right? There's a natural tendency for things to want to disperse. Right now, this is a concentrated form of gas. At the end, you'll have equal amounts, if you will, of gas on both sides. So, these are a question that you might see and stuff in terms of what is called matter dispersal. Now, remember, with matter dispersal, You've got a concentrated matter source going to a more distributed, more like broad, if you will, matter. It's no longer as concentrated. Now, if you clean your messy room, all right, you're taking all the stuff wherever it is, putting it in drawers, organizing it, whatever. Does that sound like, no, definitely Rory shaking your head. Yeah, totally. You're not helping the universe in this, basically in this context. You're making your area more concentrated, all right? It was all over the place and now it's more concentrated. That's not matter dispersal, all right? If you have a gas and you make it a liquid, do you think that's going to be making the matter more dispersed or more concentrated? Concentrated, yeah. So this is a more chemical application than just cleaning your room, all right? If you make a solid from a solution, same thing, all right? Your solutes, whatever, were all over the place and stuff, and now it's very, very concentrated. That's not going to help. But this one, eating dinner, whatever your favorite foods are du jour, you eat them and your body does what it has to do. Is that making the matter distributed or is it concentrating the matter?
Distributing.
Yeah, you're distributing it. So believe it or not, eating is very normal in terms of this kind of stuff, all right? Because you're taking these concentrated forms, whatever, putting them out. You're going to have scraps of food left over. Your body's waste, of course, is all part of this. Yeah, this is matter dispersal, man. It's so strange. This is another example, a chemical example of making your matter more concentrated. You've got water, nitrogen, and chromium-3 oxide, and you're making into ammonium dichromate, which is very, very concentrated relative to these right here. So this is one thing to think about in this section, like taking matter which is concentrated and making it more dispersed, or these other examples, taking the dispersed matter and concentrating it. And again, the ones that are more likely to occur when you have a concentrated form and you make it more dispersed, which is eating dinner, etc., etc. Okay.
Stored chemical potential energy is released from reactant molecules in an exothermic reaction. This energy spreads out or disperses over the product molecules and the molecules in the surroundings.
Earlier I said how up to this chapter, exothermic reactions have been the one which we would use to dictate if a reaction is going to occur or not occur. And now you can see why I did that. Because the other kind of dispersal is energy dispersal. Concentrated energy being distributed to the outside. So exothermic reactions have some kind of a system, the chemicals that are actually reacting. And when they react, the energy is released and it goes into the surroundings, like the water, the air, the glass container, whatever it is around it. So you started with a very concentrated energy form, and after the reaction was done, the energy is dispersed. So energy dispersal is definitely happening when you have an exothermic reaction. And that's why most of the time, exothermic reactions are the ones which are going to occur. Those are the probable ones. But you can also probably see now there's a matter dispersal component. We'll talk about how these two come together here in a little bit. Okay, so exothermic reactions with their negative delta H's, all right, negative enthalpies, those involve a change of reaction, all right? The energy goes from concentrated system to the more distributed surroundings. Energy is being dispersed, and those are very, very probable. Not 100% likely to happen, but very, very probable that they're going to occur. The energy initially you could think of as stored as potential energy, the energy that something can happen if you make it happen. And in these exothermic reactions, you're making it happen. So that potential energy is turned into kinetic energy. The energy is distributed not from just a few molecules, but to a lot of molecules, to the water, to the air, to the glass container, whatever it's around and stuff like that. So usually exothermic reactions are product favored. Usually, but not all the time. Exothermic reactions are fun. There's lots of energy involved. You see things happen. This is an example of the thermite reaction. It's very, very exothermic. That's a big negative number. Remember, the delta H negativity means exothermic and positive means endothermic. So you add a little bit of water to this iron 3 oxide aluminum example, and you end up making thermite. There's no sound with this video, but you can see it just goes crazy. You have to keep it behind bars. And we did this once in our lab in 2505, and it wiped out this metal plate under it. Lots and lots of energy given off. But in the process, then, of course, you end up with pure iron aluminum oxide.
It seems backwards that bombs have negative energy.
Yeah, I agree. I've often wondered why lots of energy given off got a negative value, but I agree, Jacob. I can't explain.
In the center beaker is water at room temperature. To this we add solid ammonium nitrate. The ammonium nitrate dissolves. Usually, a reaction that occurs so readily is exothermic, but we see from the thermometer that this reaction is endothermic. The temperature of the water drops significantly. This reaction is not favored energetically, yet it still occurs.
So in the last slide, we showed thermite. Whoa, lots of energy. And you can have like sodium and water. Boom, energies, explosions, stuff like that. Whoa. Oh boy, a solid dissolves in water. Oh, exciting, Russell. And you're probably like, whoopie-doo, right? But here's why I put this after here. This is an example of a reaction where something happens. You put a solid in water and it dissolves. And again, you're like, whoopie-doo. But here's why chemically this is exciting in this context. It's an endothermic reaction. All right, so I just went through this big rigmarole about how energy dispersal is what makes probable if a reaction happens or not. Well, this one does not have energy dispersal. This is actually concentrating the energy from a more dispersed state. If you have an endothermic reaction, which is what this one was, it went from 20-ish degrees to 11 or so, you're pulling energy from the outside in, all right? That's making energy more concentrated, and that's not probable when you look at all reactions. So in this reaction, something else is happening. Now, it's not exciting, but here's a couple of things I want to pull from this. First of all, this has a positive delta H. It's endothermic, all right? And most of the time, we would say that reaction, not very likely. But the second thing about this, something else is going on besides enthalpy to make this reaction happen, all right? If you see a reaction occur, and it can be explosions, fireworks, or even just a solid dissolving, those are spontaneous reactions, all right? The thermodynamic quantities in the world are saying, yes, this reaction's gonna go. But this one's kind of confusing based on what we've done so far up to this point, because enthalpy really doesn't want this reaction to go. It's endothermic. You're pulling energy from the outside in. So something else is happening here to make this reaction occur. So even though this isn't as cool as the other reactions we've looked at, which are very exothermic, it is happening, first of all, so it's spontaneous, and we need a better explanation than just enthalpy to understand what's happening. So this leads us to entropy. And entropy, which gets the symbol S, is literally like a counterpart to enthalpy. It's just as important. We haven't needed it to this point because most of the time enthalpy does the job. But in a lot of cases, entropy is an excellent way to see if a reaction's going to go or not. Now, we talked about how energy dispersal is basically enthalpy. This is the mass dispersal part, taking things that are very concentrated and making them kind of more disordered. So entropy is literally a measure of messiness, of disorder, all right? If you have a reaction which is going to become messy, entropy is very, very happy with it. And if you have a non-messy reaction, then entropy is not happening. So as an example here, oh, Mountain Crew cards. Oh man, I dropped them out of my hands. Spontaneous. All right, that happened. All right, cards, get together and go back in the door. Non-spontaneous, right? It's silly, right? This is, I left my magic wand at home, these kind of dumb things I say. So what I'm going to do is I'm going to take this, I'm going to kind of organize them here, get them back in that and stuff. Here they are there, I'll put it back there. That took energy, all right? So entropy, believe it or not, is what I just represented there. Throwing them on the ground, messy, no problem, easy to do. But reorganizing, getting them all together, putting them back in the drawer, that took energy. So in terms of spontaneity, things that are going to happen, throwing them on the table, easy. That was spontaneous. Putting them all back together in a nice little organized roll, non-spontaneous. So entropy literally is a measure of how disordered you are. If your room is naturally messy, hey, entropy's your friend, because that's the normal way, all right? Leaving your pop cans around or not emptying the garbage can, all these things, right? All of these things are entropy, are related to entropy. Entropy is all about disorder. Entropy was named after Clausius of the Clausius-Clapeyron equation, if you remember from Chem 222. If you don't, it's really no big deal. Entropy apparently comes from some Greek word which means transformation. I don't know. Anyway, I thought that was kind of interesting. I love his kind of side beard there. But anyway, entropy is really interesting, and it's going to be super important to us, all right? It's going to help us to start understanding when reactions will occur and when they won't occur. So that reaction where ammonium nitrate dissolved in water, it happened naturally, all right? Enthalpy didn't like it because it was endothermic. Entropy, though, was really happy with it. It was making the world messier. It's interesting how Clausius also came up with the idea how enthalpy he referred to as the giver of life, and entropy was the taker away of life. And I'm going to let you philosophize on that for a while. I'm not totally convinced of this. However, energy, of course, you need to make things happen. It's something that happens in life. And our world is based on essentially making things messy. So entropy is one way to think about that. I don't know if I totally agree with that, but there's a lot of interesting things around Clausius and life and energy. Anyway, now, earlier on Boltzmann's grave tomb there, we saw he inscribed this, S equals K natural log of W. Sometimes it's LOG, this one is LN, same kind of thing. I want to talk about where this comes from, because in terms of chemistry, this is really important. W is referred to as what's called a microstate, and a microstate is just having an atom in different kind of positions. K is something that's now called the Boltzmann constant. Boltzmann constant is not a number that you need to know / memorize, because I'm just showing it up here. In later chemistry courses, you might see it, but most of the time you won't. If you have a system with just a few microstates, you won't have a lot of entropy. But most of the things that we'll look at will have lots and lots of these microstates, and they'll have higher energy. So I want to show an example of how microstates work in chemistry, and just kind of know about it, but without actually talking about it. However, all spontaneous endothermic processes will have an increase in entropy. So that ammonium nitrate we saw dissolving, which wasn't exciting, it just dissolved, all right? It was endothermic, but it still happened. So by default, then, that has to have an increase of entropy. And it does, as we'll talk about in a little bit. Now, here's some examples. This is a molecule A, all right? And A can be in the left side, and A can be in the right side. So one single atom or molecule on the left or the right, this would be 2 microstates. It's more interesting, though, as you go up in the number of atoms. So if you have A and B, you can have A and B both on the left, you can have A and B both on the right, A on the left, B on the right, and flipped, 4 microstates. And if you have 3 molecules, you have more and more and more and more and more. You can see how the number of molecules, if you raise it to the second power, is a way to do it. However, if you start getting to Avogadro's number, oh my goodness, you have tons of these different microstates. So you have more atoms, you're going to have more entropy, the disorder of things, all right? Unless you have those like solids and stuff at very low temperatures, solids being kind of locked into place, you're going to have a lot of different microstates, which means you'll have more entropy. So chemistry is basically ready for entropy. There's so many different combinations of these things that are possible.
Molecular motions are much more random in the gas state than in either the liquid or solid states. Motion in a liquid is more random than that of a solid. Gases tend to have the highest entropies, while solids have the lowest.
We're going to see how entropy is definitely affected by the physical state of your material. And solids are very locked in place, as we've talked about it, very rigid. On the other hand, when you go from a solid to a liquid, you have weaker intermolecular forces, but there still is force involved. So these have more microstates possible. And by the time you get to gas, there's almost unlimited numbers. So look at these numbers here, which we'll talk about for entropy. Solids will always have lower entropy numbers than liquids, and liquids will always have lower entropy numbers than gases. And that's a thing we'll see kind of going throughout the class. Questions on that? All right, we'll do more of this on Wednesday. Looking forward to your class presentations. Have a great day.